Hi, welcome back to my video, and in this video I will talk about how to use a scipy.optimize function to find the roots of a nonlinear equation. And here is an example. This is an equation, and on the left hand side we have a function equal to 0. It means we need to find the root of this left side function, and I specify steps which I think necessary to use the supporting function scipy and to solve the problem of finding the root of a nonlinear equation. So the step number 1, we need to guess. What is our guess? We need to guess where could possibly the root of this function is. And to have the most efficient guess, we have to plot the left hand side function. We need to plot this function, and also we plot the right hand side function, and our right hand side function is only a constant value at 0. And after we plot both of them on the same plot, we will see the intersections, and their intersections will be the approximate solution to our given equation here. And finally, after we have our guesses of where the root could be, then we can use the supporting function to find our roots, because according to the algorithm using in this supporting function, we need to have a good guess. Otherwise, our supporting function might not convert to the solution. So let's go next. And here I write the code for the first step. And before doing anything, we need to import necessary library. The first is NumPy, next is matplotlib for plotting our function, and finally is the supporting function from scipy. And as we said, in the first step we need to plot in order to have the guess about where the solution to this equation might be. So first we need to define the left hand side function, and this is our left hand side function. You could say this is the function with the independent variable x, and this is our function. The comment in the line number 11 totally equivalent to the line code of define fx. It depends on your preference. You could use either the comment or the command in the line 11, or you could use explicitly define the function itself. I prefer the explicit way. It's easier to understand. And I also have to define the derivative of our function, the derivative of this function. It is necessary to use the supporting function scipy.optimize to find our root. And finally, those are the two lines in order to plot our two functions in the same plot. This is the plot of our left hand side function, and this one, because the value on the right hand side is only a constant value 0, so we just need a line at y equals 0 for all of the x value. So that's why it's only a line along the x-axis. After we done with the first step, we have our initial guess. So this is the plot that we obtained from the first guess, and this is the line x equals 0. No, sorry, this is the line y equals 0, the right hand side function, and the blue curve is our left hand side function, and where they intersect here or here. Oh, sorry, maybe more exact, it should be here. Do we have any eraser? Yes, we can erase this one. And then let's go to the pen. Yeah. So this is the right hand side function, and the blue curve is the left hand side function. They intersect at this point and at this point. So we have our initial guess. We know that this is the x-axis and this is the y-axis. And in order to use our supporting function, this is our supporting function, optimize, and the method I choose to solve or to find the root of this function or to solve this equation is the Newton method. And the first input to this one is the function that we need to find the root, which is our left hand side function. And then next is the independent value at which we need to find the root. The independent value here is the x value. So as we could say, this is the first root, and what is the x value of this first root would be around in this interval. So I said maybe it will be around -3. And then next is the derivative of our f function, which is very necessary for the convergence of the Newton method in order to obtain our root. And this is the tolerance. And finally is how many, the maximum iterations that you want the Newton method to continue to find the root, because the method will have a loop and all iteration for many times. Some cases the method doesn't convert to a root, that's why we need to have a maximum iteration in order to stop the method when it doesn't convert to a root. Because we have two, you could say that we have two roots, that's why we need to use the supporting function a second time, and we only need to specify the other x coordinate of the other root, and I guess maybe it will be around somewhere 2, that's why I put it 2 here. And that's all. This is the step 2, and we will got our solution. So now I will run the code. I already prepared the code in Google Colab. So let's run the code. This is our first step in order to plot our equation, the left hand side function and the right hand side function in the same plot. Let's run it. Okay, now we have the plot here. The command here is order to save our plot. Here you could see the folder symbol and the plot is saved here. So if you want to download to your computer, you can do that. So as I already explained, we have two roots around -2 and the other one will be around 2. So -3, sorry, and the other one will be around 2. So this is the second step where we use our supporting function and the method Newton in order to find the root. And let's run it. Okay, this one is -3 and the second root is 2.09. And in order to check whether those values are good, I will plot those roots which are returned by the supporting function optimize scipy with the method Newton in the same graph, with this graph. So here, let's run it. And you could see I plot the two roots as the two red dots, and they exactly where we got the intersection between our function and the left-hand side function. The left-hand side function, which we need to find the root. We need to find the root means the right-hand side is the y equals 0 here. They intersect exactly at the two red dots. And I already put the link of the code in the comment section. So, thank you for watching. I hope that it will be useful.